Hey, all, here's my conversation with astrophysicist Paul Wallace from my radio show, which we do on Fridays. I forgot to start the audio recording right at the beginning. Sorry about that. It was well worth it. There is a Facebook Live video of it. You can find that by going to my profile on Facebook. But thanks for listening to the podcast. I so appreciate it. And I'm sorry it's all been so much from the radio show, but really jammed up with all the VOCOM and good work going on right now. But here it is, Paul Wallace and me talking about all kinds of fun stuff. Thanks for listening. Sororities that go off hazing people, sometimes the degree programs and the
and like medical schools are terrible about it too.
Yeah, terrible.
Not just physics, science PhDs.
Well, back to your science PhD. You earned a PhD in nuclear physics from Duke University.
That's right.
That's impressive. Right. What is nuclear physics? What is that? I mean, I always refer to you as astrophysicist Paul Wallace. What is
I sort of made a transition after. I applied to 6 graduate schools, 5 in astronomy and 1 in nuclear physics, and none of the astronomy ones took me, but the nuclear physics one did. So I went there. But when I left, I returned to astronomy. But you asked the question, what is nuclear physics? Well, basically, it's a study of the physics of atomic nuclei. You've got your electrons. You've seen the little pictures, little atomic physics pictures of the electrons, like little planets swirling around the nucleus. And that nucleus, actually, the physics going on there is pretty interesting and also practical for both violent purposes and nonviolent ones. So both in medicine and, of course, in the fighting of wars. And that's where it's first applied, You learn some new physics in the first application, and this didn't start in the 20th century, but the first application of new knowledge is always in the fighting of wars.
Wow, is that true? I mean, that's just true across the board.
Not entirely, but almost.
Wow,
yeah.
That's
like before Galileo turned his telescope up to the moon, he sold it to the Venetian Senate so they could use it to spy out the horizon to see approaching ships, unfriendly ships on the horizon before anybody else could. And then only then, after he made his buck, did he decide to, hey, wonder what I could see if I turn it up there.
Isn't that interesting? Only then did it become part of like the pursuit of science itself, or to answer humans' greatest longings. 500 years ago.
The Venetian Navy found it very, very handy.
Well, your bio goes on, my friend. I'll quit bragging about you in a moment, but that you were twice awarded the NASA Faculty Fellowship at the Goddard Space Flight Center in Maryland.
Right, and each time was for 2 years, but I only was able to go 3 out of the 4 years that I was awarded to me for.
Well, so I bring up all of that because we get to hear you on Friday, and you're just you're such a down to earth guy, and we spend so much time talking about rudimentary things around here, because Hunter and I don't seem to know anything about anything when we have you on the show, and I like having you on Friday. It helps. This is going to sound a little ironic, and it's meant to be. Talking to an astrophysicist in these political days feels a little grounding. It feels like
really, it does. It changes it opens up your mind sort of in a different direction.
Yeah, normally, we do a lot of politics on this show, and I do a lot of that in my life, and talk a lot about like faith and human engagement and the human dilemma, and how we live with each other and how we fight each other, these kinds of things. Normally, when you have an astrophysicist around your life, you're like, boy, that astrophysicist, she blows my mind. But now it's like, I can't wait to talk to the astrophysicist and get down to earth here, because the political and how we are with one another in this world has gone so...
and let your pulse return to a resting sort of rate.
Yes. It's also quirky.
Yeah.
We need to talk a little quirky. That's my science joke for the day.
Let's talk quirky. I got a couple quirky stories for you.
I wasn't. I was just making a quark pun.
That was funny. That was funny.
Is that the way a physicist laughs at a joke?
Yeah.
A physicist laughs at a joke just by saying that was funny. That was definably funny. That's perfect. It's the physicist cackle right there. So tell you that's funny. Well, what do you have on the docket for us today, Professor?
Well, 2 stories, actually 3 stories. One of them I got to put out there just to share with our listeners. A small anecdote about the poor state of science education. I won't go too long with this because I know you're trying to learn science here, but my daughter is a 11th grader in the local public school here, in Atlanta, and it's not the greatest school, but it's not the worst school, and it's an international baccalaureate school, so she's sort of on the nerd track. She's got one class that's not sort of IB or AP class, sort of only one class that's not sort of a nerd class, and it's her physics class. And this guy tried to convince 11th graders of this, that if you took the sun and weighed it against all the planets in the solar system, that they would be equal, that they would balance out.
Okay, now I know that's supposed to land like
a. Not true.
I know that's supposed to land like a thud, but I'm not gonna. I don't know if I can speak for Hunter, but that would be the kind of thing I would believe, and that would be the kind of thing I would say. Okay, so why is that not? Why is that not? Why to a physicist is that so obviously untrue?
But it's not okay for a scientist to teach it because.
Okay, all right, fair enough.
Because like 99.9% of all the mass in the solar system is in the sun. It's pretty much all the sun.
Really? Okay.
99.9%
of all the mass is in the sun.
Yeah, between 99.8 and 99.9% of all the mass in the sun of all the mass in the solar system is in the sun. And and this guy who's teaching physics to 11th graders is telling them that they would anyway. I just had to put that out there.
Yes, yeah. It's been eating at your cross since your daughter came home and said, "Dad, is this true?"
No, she texted me in the middle of it. She texted me in the middle of it, and I said, this is like 18th century knowledge here, and anyway,
that is woeful.
I just thought I'd throw it in there to let you know that the world is in fact going to hell.
Well, okay, so I think it's already there, and it turns out that hell is in the middle of the sun, and people can't tell why it is. But even when you made the comment about you being a nuclear physicist, which you are, that you said when you look at those pictures of what a nucleus looks like in the center of an atom, I remember learning as an adult that image that I was given of an atom as a child, where there was a nucleus with something in the center, little hard balls flying around, that actually not really like that. That's a useful sort of
not
pictorial metaphor. But if you need to know things about physics, that's not actually it. And that's the real trouble with science, isn't it? That boy, a lot of us are just convinced of things that we were taught and told. And I'm sure some kid is going to go on the rest of his or her life telling people that half of half the weight is the sun and half the weight of the other planets, and that's why the thing stays level. Yeah.
Yeah. Well, I tell my physics majors, usually majors, I tell this to, is that your education is basically a matter of learning that the things you learned before aren't quite really true. And so those are two things.
Keep taking courses so that you can keep unlearning the things that we previously taught you. That sort of logic.
Right. All that stuff we spent the entire last year talking about, that's not really the way things are. Well, and then what I don't tell them is that what I'm telling you right now is not really the way things are either. You have to wait till next year to find out.
That's right. You'll find out that it wasn't exactly as your mind put it all together. And that is, I do think you're right that that's one of the things that I think has made science a difficult topic for a lot of people. Is that there's two things that seem to me happen for people in science: that we don't often know, and we don't know very much, and somehow we feel lesser than if we say something that's not true when it comes to science, and that feels like it just pins people in. Somehow to be wrong about science.
Students are very afraid to be wrong, and I attribute that partially, and again, I don't want to get too political here, I attribute that partially to our national obsession with testing students to death as they're coming through their public school years. But by the time they get to be college, they're really, really, really scared of being wrong. And I try to tell my students that they'll never do they'll never do anything new or creative or worthwhile if they're afraid of being wrong. If being wrong is the worst thing you can be, then you're never really going to.
I love that.
Create something new.
I mean, that's sort of the heart of science, isn't it? Is that you the point is to find out where you're wrong. That's
exactly.
That's the heart of the scientific method. I remember I used to have a show on this very station, AM 950, the Progressive Voice of Minnesota, on Sunday mornings, a little religious show, and we were followed by the atheist group, and they were fantastic. And we would share Christmas show together. It was always my favorite, the religious show and the atheist show doing Christmas show together. And that was one of the things that August Berkshire, the host of that show, would often say. He said, Doug, the difference between science and theology is, in theology you're always trying to show how you're right, and in science you're always trying to show how you're wrong. And anyway, we can talk more about that here after the break, because we are going to go into a break and then get back with astrophysicist Paul Wallace here on AM 950, the Progressive Voice of Minnesota. Here at the
I do. One of them has to do with Saturn.
Okay.
Visible in the evening sky these days.
So much. It's
Atlanta
so cool.
and from Twin Cities. And what you may not know about, there's a lot of cool stuff about the solar system that maybe most people don't know.
Yeah,
and
all the things that are cool
Saturn's
about the solar
North
system
Pole,
I don't know.
At Saturn's North Pole, there's a huge hexagon shape. I'm not making this up. It's if you look down at the North Pole of Saturn, the clouds sort of come in different colors, and there's a big, basically, right around the North Pole is a huge hexagon,
really?
Thousands of miles across.
Like the Dharma Initiative on Saturn from the TV show Lost. Like the Dharma Initiative on Saturn from that show Lost back in the early 2000s. Okay, Paul, so here's where I get hung up already, and you have to be gentle with me.
All right.
How by what instrument do we look down on the North Pole of Saturn? Is that a...
Well, Cassini is the name of it. It's an orbiter that's been out there for a long time. The mission is now officially over, but we're still sorting through the data.
And it's orbiting Saturn, particularly this telescope.
Yes, Saturn, and investigating its many moons and its fantastic system of rings, and it has gotten a good look at Saturn's poles. You can actually see them from the Earth, but only at a very slight angle. But it got a good look at this hexagon, and apparently this hexagon is quite tall. It's hundreds of miles high. This was something we didn't know before.
What do you think it is? What makes up this big hexagon on the northern pole of Saturn?
Well, we think it's just cooler. First thing you have to know about Saturn is it's a big ball of gas. Okay, so it's not like there's a surface you can walk around on, and it's a big ball of gas. It may have a core way down inside that's rocky, but it probably doesn't. It's probably a kind of liquid core. So the clouds themselves, sort of, if you look at the pictures of Saturn, you'll see that that it's streaked with clouds. Just it's got clouds streaked across it, and at the poles, these streaks become circles as you get closer to the pole. But this is not a circle; this is a hexagon. Wow! And it's always strange. Nobody quite knows what's causing it, but it's one of my favorite things in the whole solar system, and because it's obviously, and it's not. It's very symmetric. You know what I'm saying? It's not a hexagon that looks sort of out of whack. It's like really symmetric. All the sides are the same length, and it looks like,
it's designed
very,
somehow. It's
very surprising. Yeah, we've known about it since 1981.
So you're saying there's a particular design element there that seems peculiar in the known verse.
Right. Not often do you find such obvious, clear, clean geometric shapes that are thousands of miles across.
Do you think it was the Aztecs?
So I think it's the who?
Do you think it was the Aztecs? I'm just kidding. When they find those places.
I like the theory. I like that.
That the Aztecs were first on Saturn. They were already there. That's right. They were already there, and they created that. Hey, do you have a question, or do you have time for a question from on quantum physics or quantum mechanics? Hey, Brad in Robbinsdale, your question or comment for astrophysicist Paul Wallace.
Yes. I guess we are all familiar with sort of this macro world that we live in, but by my understanding, at the quantum level, at the atomic level, all our notions about time and space, cause and effect, before and after, just go out the door. So I'm curious about that. Plus, also, by my understanding, all that we know about, the quantum world, since we cannot observe it, is through some type of higher level, sophisticated mathematics. And I was wondering if you could speak on that.
Yeah, I'll answer the second one first. Yes, it is. We can observe it, but not like we can look out and see a rainbow out the window or something. We observe it with all manner of technology, but to understand it, to have any notion of how to wrap your head around it, you've got to do mathematics. And after you do math for a while, you sort of can get sort of an intuition about how math connects with. In other words, you can look at an equation and you get a sense of what's going on from an equation. You can get a sense of what's going on physically. Now, in the macroscopic world, you've got the thing itself right in front of you, so it's really easy to do. But as you get smaller and smaller, you really have to let the mathematics guide your knowledge, guide your understanding and your intuition about what's going on.
Do you think the
trouble with that, with quantum mechanics, is that as you get smaller, a lot of our normal rules do, in fact, in a sense, go out the window.
Yeah, it's really something. Paul, how do they? Brad has dropped off the line now, but so I'm going to follow up on this question. If it's normally that in any kind of knowing or understanding or physics, you would test your theory against what's actually happening in this quantum mechanics and quantum advanced math. What is the basis by which the math is being tested to know if the...
Oh, well, you can make observations.
Okay.
That's a good question. You can make observations. They're rarely so direct as in, like, watching planets move around the sun. It's less direct than that, but you can make distinct observations. You can investigate, again, like I said earlier, atomic nuclei in great detail. If you sort of let the theory guide your imagination a bit, you can really see what's going on. And quantum mechanics, I need to say this, is a experimentally, extraordinarily well supported.
Okay.
It is not like string theory is right now, which is not well supported experimentally. Quantum mechanics is a 100-year-old theory now almost, and it has been subjected to every possible test, and experimentally, it's on excellent grounding, excellent footing.
All right, now Brad's not on here, but I want to extend his question. Maybe this is what he's getting at. Back in the early 2000s, there was a movie that I saw and a whole movement of conversation, and the movie was called What the Bleep Do We Know? And it took physics learning, especially quantum physics learning, and where like time is not the way that it is here and the past and future are different, and applied that then to a way to understand human interactions and to say, like maybe the way we now think we can know the past and only predict the future, maybe we can flip those around and affect the past and only be able to, have a thought about the future. This kind of thing. Is there anything to that where people took physics and then applied it to spirituality or to human life or to relational dynamics and all that?
Yeah, I know the movie, and my feeling about that is that physics might provide a nice metaphor for things like that and ideas like that. But as far as that really, technologically we can't do things like go back in time.
I got you.
Maybe one day we'll be able to, but right now we can't. So it's very speculative. In other words, the physics provides a nice analogy for maybe some spiritual ideas, But as far as it being a real connection between the two, I'm skeptical.
Well, that's astrophysicist Paul Wallace, our Friday guest. We didn't even get to the third topic. Good thing we're around next week.
No, it had to do with neutron stars and faster-than-light motion.
Faster-than-light motion? Oh, my gosh.
Yeah, not really, but it looks faster than light.
That's even better. A head fake, a faster-than-light head fake. Hey, that's Paul Wallace. Hey, Paul, thanks so much. We'll talk to you next week.
All right, see you, Doug.
All right, we'll be back here after the break. AM 950, Progressive Voice in Minnesota.